These are your 4 or 5 notes on scatter plots and lines of fit. So we're going to talk about what a scatter plot is, and it's a statistical representation. We're going to talk about using that data to draw a line of fit, and then once you have a line of fit, you can use that to help you make predictions in the future, go back in time. So bivariate data is data consisting of 2 variables. Bi means 2, so bivariate means 2 variables. A couple examples of things that we compare in the real world. Time goes with a lot of things. So time and temperature, you could be talking about in a month's time, in a week's time, in a year. Height and shoe size, somebody's height, and then their shoe size. And then years and population are 2 different variables that we could compare things to. You could be talking about population of people or population of animals, a specific species of animals, all that sort of thing. So 2 variables. When you compare 2 variables, you're kind of looking to say, hey, is there a relationship with these 2 variables? And so a graphical display of that would be a scatter plot. And it shows a relationship or a correlation of 2 variables graphed as ordered pairs. So you take your 2 variables, you decide which one's the independent, which one's the dependent, and then you just start recording your data. It doesn't always look pretty in exact straight line with a constant rate of change, but the data could possibly show a relationship. And so there's a couple different ways that can occur. So you have the 3 pictures in the middle of the screen are like examples of scatter plots. So the first 2 show correlations of the data. The first one is a positive correlation because it has a positive slope. The dots are rising as they go from left to right. The second graph is a correlation. There's a relationship there. The dots are lining up, sort of, with a negative slope. They started out high and then they're ending up low. They don't fall in specific line. It's not always pretty. In real life, a lot of the data is not pretty in a straight line. And so when you make these comparisons, you try to figure out a line that is the best line to model all the data. So we call that the line of fit or a trend line. And someone just decides somewhere in the middle of that data. If you look at that third option, there is no correlation there. They're all over the map. And so someone decided to compare 2 variables that have absolutely no relationship whatsoever. And so those 2 things we wouldn't discuss anymore. When you have a correlation, though, you can look at the information further. You can go back or in the future or back in time and make predictions. So linear interpolation is when linear equations are used to predict values inside the range of data. And then linear extrapolation, that's a big word, extrapolation, is when linear equations are used to predict values outside the range of data. So in interpolation, maybe I wanted to know at this point right here what that is. And so that's within my data set. I have points before it, I have points after it. It actually shows up on the graph. That would be an example inside the data. That would be linear interpolation. Extrapolation would be something later on. And so say down the ways a little bit. Maybe I want to know what happens way down here. And so I'm extrapolating, I'm going extra. Think of like extraterrestrial, outside of the data set. So extra means outside. And so it's not one of the points I picked, but based on the pattern of all the points I picked, I could make a prediction if I kept going or if I had an equation to plug it into. So that's what you do. You come up with an equation. Now there's so many ordered pairs, you would just pick 2 of those ordered pairs on that line of fit. And your line of fit and my line of fit might not be the same. It's just a guesstimate, but it's a line. We try to linearize the data. So if we determine whether the scatter plot has a negative, a positive, or no correlation, if it does have a correlation, we want to explain it in context of the information. So anytime we read graphs, we should read the title. So this is computer sharing. These are the number of students sharing computers in these years. You can see they don't line up exactly in a line, but there's a pattern that the data is going in a downward slope. And so this would be a negative correlation. And a negative correlation says as the years increase, or as the years go on, as time goes on, the number of students sharing goes down. So the less and less students are sharing computers, which makes sense. So it decreases. That makes sense because in 2000 or in the 1990s, this would be almost like 1998, 35 students were sharing computers. That would be like one computer in the classroom. And then as time goes on, they have different concepts. Now, depending on what classroom you looked at, the data is not going to line up exactly as the same. So that's why they're all over the place. If you look at the second example, we're talking about wages, so money earned, the hours worked, and then how much money is earned. And I can see that these are very slight, but they are lining up in a linear pattern. So this would be a positive correlation. And to describe the pattern, the more hours worked, as the hours increase, the wages also increase. It's an increase relationship there. Where in the negative, it was an increase of time, but a decrease of the computer sharing. So when we're using a linear function to model data, we are going to do the same thing we have been doing for the last 3 sections. You're going to make a scatter plot. We're going to determine if any relationship exists. You draw a line that seems to pass close to most of the data points. You can't connect them all. It has to be a line. Use 2 of the points on the line of fit to write an equation for the line. And so that's where we would use either y equals mx plus b or y minus y equals m times x minus x, either one, to come up with our equation. You're going to have 2 points, so you're going to have 2 ordered pairs. You plug them in, find slope, do all that stuff that we've already done. Then we use that line of fit. We use that equation to predict data. So after you have your line of fit, we use the equation to make predictions. So this example here is about roller coasters. Shows the largest vertical drops of 9 roller coasters in the United States. So not from the same park. We don't know what 9 roller coasters they have, but all over the U.S. And the number of years after 1988 that they were opened. So from 1988 and then the years progressing, the height of the vertical drops. And so that vertical drop is that first hill of the roller coaster. So I have a table of values. Those are my 9 roller coasters there. And they're talking about time, years since 1988. So this 1 would represent 1989, and 3 would be 1991, and so forth and so on. And then it gives us the heights in feet. So I'm going to change my scales. I'm going to count along, since I got to get to 15, from 1. My range of values is from 1 all the way up to 15. I'm going to count that. I think I can count that by ones. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I can count the bottom by ones, but I'm just going to label every other number so that's not so crowded. So it looks like I'm counting by 2s, but I'm really just counting by 1s. And so I'm going to label that as years since 1988. And along the vertical, I'm going to break my vertical. Since there's no vertical drops under 151, it doesn't make sense to waste all that time. By breaking it, it tells the reader that reads this data that I broke the graph and that you just got to make sure that you understand I'm not counting the same. I'm starting at 150 and I'll count up to 400. So I think I can do that by probably by 25. So this is going to be 150. And then I can do 25. So I'll say 175. Then I'll skip it, go to 200, 225, 250, 275, 300, 325, 350, 375, 400. I could probably even count it by something different, but that's okay. And so that is my feet, vertical drop. So that's the hill in feet. And these are roller coasters, right? All right, so when I graph the data, 1 and 151, it's right about there. It's just an approximate. 3 and 155. So they're not going to line up super nice. 5 and 225. But what you'll see is probably a pattern here. 8 and 230. I could see the pattern already in the actual table. 12 and 306. And 12 and 255. Okay, now do you see how two of them at 12 had two different heights? Because we're talking about two different roller coasters. That can happen. That 12 years since 1988, in the year 2000, two roller coasters were built. One had a vertical drop of 300 and the other one had a vertical drop of 255. That's why they're all messed up. And then a year later, in year 13, years after 1988, there was another one that was at 255. I think I actually graphed that wrong. So 255 should have been here. I'm going to erase this one. Oops. 255 and 12 and 312. There we go. And the last one, 15 and 400. You do see kind of a trend, and if they were to use more roller coasters, you'd probably see the trend even greater. It is a positive trend. It's not super steep, but as the numbers are increasing at a gradual rate. I know we went up to 300 here and then only 255 here, but it was still higher. As the years beyond 88 increase, as time goes on, the vertical drop increases as well. So this is a positive correlation. And we will just say exactly what I just got done saying there. As the years increase, the vertical drop increases. That's the relationship. Identify the independent and dependent variables. So the independent variable would be years. Time is always independent. Can't change time. And the thing that depends on the years would be the vertical drop. You kind of need to decide this before you make your graph, because your independent has to be your x and your dependent has to be your y. Got to draw a line of fit. And so when we draw a line of fit, this is where we could all be different. So we got to make sure that we're all going to be the same. So I'm going to draw a line of fit right about here. And I'm just going to say that it went through that ordered pair and that ordered pair. Do you see how if you drew your line of fit differently, you're going to have a whole different slope, whole different y-intercept, and your whole different equation. So we want to make sure that our line of fits are the same. Oh, it looks like it said, I drew a line of fit, use a line of fit to write an equation in slope-intercept form. So they're actually telling me use these two ordered pairs. So I probably should have made my line go through those two ordered pairs. So 2 and 150 and 12 and 300. So I was kind of close. So we'll just use these two ordered pairs, even though my line of fit's a little bit off. We're going to say that those two ordered pairs lie on that line of fit, and we'd write an equation. So I like to use my point slope, y minus y equals m times x minus x. Before I can use that, I have to find the slope. So over here, I'm going to find the slope. Y 300 minus 150 over 12 minus 2. 300 take away 150 is 150. 12 take away 2 is 10. And so that's 15. My slope is 15. Then I just pick one of the ordered pairs. I like 2 and 150. So y minus 150 is equal to 15 times x minus 2. Distribute. I'm just going to do that over here. I ran out of room. Y minus 150 is equal to 15x minus 30. And I want to put it into slope-intercept form, so I'm going to add 150 to both sides. And so my equation, y equals 15x plus 120. And when I go through this, use the equation to determine the vertical drop of a coaster in 1998. So in 1998, that's actually time in years would equal 10 years beyond 1988. So actually not my y, my x value would equal 10. So I use my equation. I plug in 10 for my years, and we're saying in 1998, 150 plus 120, the vertical drop of a coaster built in 1998 would have been 270 feet. That is called interpolation, because the 10 years, 1998, should be on my graph. So if I go up to 1998 on my graph, which was 10 years, and I come up to the graph, and then I go over, about 275, so 270, just depending. My line of fit isn't exactly accurate with my equation. So that's about right in the vicinity. These are all approximates. And then the last thing we can do is use it to figure out the vertical drop of a coaster in 2016. 2016 isn't on here, but that's 16 years past 88, or 2000. 88 is 12 years from 2000, so you take the 16 and the 12, that's 28 years beyond 1988. And so y equals we plug in our 15, we multiply it by the 28, and then we're going to add 120 to it. So 15 times 28 is equal to 420, plus 120 is giving us a vertical drop of 540 feet. Now, in this data, that's called extrapolation, because I don't have 28 years beyond 1988 on my graph. So I'm going above and beyond in the future. Since 2016 has already happened for us, we could actually look it up and see if there were any roller coasters that had a 540 feet drop or not. Lesson summary here. Gave you a freebie. Happy Thanksgiving from me. And all I need you to do is draw an example of a negative correlation graph. Just a quick sketch. Good luck.